Welcome to iLectureOnline, and as I promised, here's another example of how to deal with momentum and energy in the same problem. So we have a 10-gram bullet which is fired into a 4-kilogram wooden block sitting on a horizontal frictionless surface. The block with the bullet slide towards, so that would be after the collision of course, and also assuming that the bullet stays stuck in the block. So the bullet and the block slide towards a frictionless 30-degree incline. The block with the bullet slide 12 meters up the incline. Then the question is, how fast was the bullet moving before it collided with the block? Sounds like an interesting problem, doesn't it? Let's draw a picture to kind of get a feel of what's going on here. So I have a bullet that is fired into a wooden block that's sitting on a frictionless surface. And the velocity initial of the bullet is what we're looking for. We don't know what it is, and that's what the question asks. How fast was the bullet moving? The bullet gets fired into the block and stays stuck in the block. And then the bullet and the block together will slide to the right with some V final after the collision. And until the block and the bullet then reach an incline and they start sliding up the incline and they reach a height of, we don't know what the height is, but they reach a distance. The distance equals 12 meters before the block comes to a stop. So the question then is, how high did it go? And then finally, how fast was the bullet moving before it hit the block? All right, where do we start? Well, this is a chapter of momentum, and we know that momentum is always conserved in any collision. So when the bullet and the block collide, at this point, momentum is conserved. So we can say that momentum initial equals momentum final. So m of the mass of the bullet times the velocity initial of the bullet plus the mass of the block, and I'll let m, the big M, be the mass of the block, little m be the mass of the bullet, times the v, and I'll use big V for the velocity of the block initial, equals the mass of the bullet plus the mass of the block, because they are now together. It's therefore an inelastic collision, times velocity final, which is the final velocity of the block and the bullet as they slide to the right after the collision. Now right away we realize that the block wasn't moving when it got fired into, so that is equal to 0. So we can say that, m v initial equals m plus big M times v final. And then finally, dividing both sides by m, we can then say that the velocity initial of the bullet is equal to the sum of the masses of the bullet and the block times their final velocity divided by the mass of the bullet. Now we don't know the final velocity of the block and the bullet because we don't know the initial velocity of the bullet and the block. But they do give us a hint. They say the block keeps sliding, it's frictionless, so unless some other force comes along, the block would just continue to slide forever. But then it gets to an incline, goes up the incline, a distance of 12 meters before coming to a stop. So then you could say, after the collision, we have what we call a conservation of energy problem. The initial kinetic energy, as it's sliding up down the flat portion here, then turns into potential energy as it goes up the hill until all the kinetic energy is converted to potential energy and the bullet and the block stop. And let me draw the little bullet in here because it's in there. There we go. All right, so we can say energy initial equals energy final. Now of course we cannot use that for the collision itself because it's an inelastic collision and energy is not conserved here. But it is conserved after the collision. So energy initial, that would be the kinetic energy initial for the block and the bullet, equals the potential energy final as it stops up the incline. Kinetic energy is 1/2 mv squared, but the block and the bullet are combined, so we say 1/2 m plus big M times v initial squared. Now, that's not the same v initial as we had over here. That's the v initial of the second part of the problem. So make sure we keep that separate. And that equals the mgh, m plus big M, because the masses are combined, g times the height that he gained. Now, how high did it go? Well, we know that the incline is 30 degrees. And so theta equals 30 degrees. We know the distance is 12 meters, so we can actually figure out the height from trigonometry. We can say that the height is equal to the hypotenuse distance times the sine of the angle theta, because it's the opposite side to the angle, so times the sine of theta. So height is equal to 12 meters times the sine of 30 degrees. And the sine of 30 degrees, that's 1/2. So height equals 6 meters. So we do know the height now. That can be plugged into here. Now notice the initial velocity of the mass and the block, the block and the bullet together as they're sliding down the side here, sliding down the horizontal portion. That velocity initial really is the same as the final velocity after the collision. So if we can solve this portion of the equation for the initial velocity of what the block and the bullet had before they slid up the incline, then we can put that in here, and then we can get the initial velocity of the bullet. Okay. Does everybody see that? That the final velocity after the collision becomes the initial velocity of the second part of the problem. All right, so let's solve this equation for V initial. We do have an m plus m here, we have an m plus m there, they cancel out. Multiply both sides by 2, we get V initial squared is equal to 2gh. And then we can say that V initial is equal to the square root of 2gh. And that can then be substituted back into this equation. So let's go ahead and do that. So we have V initial is equal to m plus big M times V final, which is the square root of 2gh, all divided by the mass of the bullet. And now we can go ahead and solve for the initial velocity of the bullet. So this is equal to the small mass, which is 10 grams, 0.01 kilogram. Remember, there's 1,000 grams in a kilogram, plus the block has 4 kilograms of mass, times the square root of 2 times g, which is 9.8 meters per second squared. H, we discovered, was 6 meters. And now take the whole thing and divide it by the mass of the bullet, 0.01 kilogram. All right, now, grab your calculator. Let's see what that's equal to. So we have 19.6, 2 times 9.8, times 6 equals, take the square root of that. There we go. Then we multiply that times 4.01 equals, and divided by 0.01 equals. And, wow, that's quite a velocity. Let me try one more time, just to make sure I didn't make a mistake. 19.6, 19.6. We multiply that times 6. We take the square root of that. There we go. Sounds about right. And then we multiply that times 4.01. And then we divide that by 0.01. That's the same as multiplying times 100. And sure enough, wow, that's quite a velocity. Of course, I came up with the numbers myself and wasn't quite sure what we're going to end up with. So we have 4,300, and let's round it off to 50 meters per second. That's definitely a supersonic bullet coming out of a very big gun. But hey, it's all physics, and that seems to work. So, recapping what we just did, we had a situation where a bullet collided with a block. Since there's a collision, we're going to use conservation of momentum for this part of the problem. Then, as soon as the bullet and the block are moving to the right on a horizontal frictionless surface, and then up an incline, eventually stopping, this situation here, we have what we call a conservation of energy. So we write the conservation of momentum for this part of the problem, the conservation of energy for this part of the problem. Now we realize that we can find the final velocity in terms of what happens initially through this equation, and that ends up being this right here. So the, I'm a little bit too far ahead. So the initial velocity here of the bullet can be expressed in terms of the final velocity of the block and the bullet after the collision. But since we don't know either the initial velocity of the bullet or the final velocity of the block, we're kind of stuck there. But on the second part of the problem, we get some more hints. We do realize that the block and the bullet slide up an incline a distance of 12 meters. So using the conservation of energy, we can figure out what the initial velocity is of the block and the bullet before they slide them incline, and remembering that the initial velocity of the second part of the problem is equal to the final velocity of the first part of the problem. So once we solve for the initial velocity here, we plug it into the final velocity there, and we can then solve for the initial velocity of the bullet. And that's how you do these types of problems. Okay, give that a try. See if you can come up with the same result.